For this lecture, I wanted to do something a little different. Instead of typing all of this information into a Word document, I thought I would take advantage of the graphics that are in the textbook. So if you look at section 3.1, in section 3.1, we're going to get into applications involving the first derivative. And we will use the first derivative to figure out where a graph maximizes and minimizes. And keep this in mind. Remember that the derivative is the slope at a particular point. So let's say that we have a curve that looks something like this. And I want to know, where does this curve reach maximum and minimum values, also known as maxima and minima? Well, I would want to know, where is the derivative equal to 0? In other words, where would the tangent line have a horizontal slope? So if you look here, for example, that's a terrible picture. Let's try again. If we were to look at this point here, for example, we could almost envision a horizontal line here that would have a slope, of course, of 0. And also somewhere in here, we would have the same situation where the slope appears to be 0. So what does that tell us? Well, it tells me that anytime a graph reaches a maximum point or a minimum point, the derivative is probably 0. It can be undefined, and we will probably look at some cases where that occurs. But for the most part, we're going to depend on the first derivative being 0 and sometimes undefined. So let's take a look at the bottom of this page here and see what the author wants us to understand. The first thing we have here is increasing and decreasing functions. And I want to walk you through the notation, because when you first read a calculus textbook, it can seem somewhat overwhelming. And I hope that I can explain in a way that makes the notation less intimidating. If you notice the graph on the graph on the left is considered an increasing function as x goes from A to B. Notice that x is A at this location and x is B at this location. And notice that f of A, which is the y value, notice that f of A is less than f of B. Well, since f of A is less than f of B, then we have an increasing function as x goes from A to B. If you look at the picture to the right, notice this time that we still have the same interval, right? We're going from A to B. But in this case, we note that f of A happens to be higher than f of B. And that tells me that we have a decreasing function as x goes from A to B. I hope that explanation was clear. If not, you can fall back on the book's definition. And the definition says a function f is increasing over an interval I if for every a and b in the interval, if a is less than b, then f of a is less than f of b. A function is decreasing over an interval I if for every a and b in the interval, if a is less than b, then f of a is greater than f of b. To me, this can be somewhat intimidating. And if you'll fall back and look at the description we just did on the prior page, I think that it's a little easier to understand. Let's talk about Theorem 1. Theorem 1 says, let f be differentiable on an open interval I if the derivative is positive or greater than 0. If the derivative is positive for all x's in the interval, then the function is increasing on that interval. Likewise, if the derivative is negative or less than 0 for all values in the interval, then we would say that f is decreasing on that interval. So here we have a function. F of x is equal to 1/3 x to the power of 3 minus x plus 2/3. And this is a cubic, and cubics generally have this shape where it starts low and usually wiggles around and ends up on a high note. But notice that as you travel, and we always rate our graphs from left to right. That's something that hopefully was emphasized in high school. But when you read a graph, we read from left to right. So if we start, say, at x is -2, if we look at x is -2, if we were to visualize a tangent line here, notice that that tangent line would be positive. In other words, the derivative is positive. Also, if we look at, say, -1.5, the x value at -1.5 or very close, again, notice that if we try to sketch a tangent line there, that would be positive. But what happens when we get to -1, the point -1, 4, 3? Notice here, we have what appears to be a horizontal tangent line, which means the derivative is 0. And then we could visualize tangent lines that are negative between -1 and 1. And suddenly, when x becomes 1, we have another horizontal line, which means the derivative is 0. And then from 1 to infinity, no matter where we pick an x value, it appears that the horizontal lines are positive, which means the derivative is positive on that interval. So what have we just shown? Well, if we follow the purple here, we have a positive derivative as we move up the incline. Then we have a 0 derivative as we reach a maximum value. And then going down, we have a negative derivative. And then suddenly we hit x is 1 and we have a 0 derivative. And then we have a positive derivative from here on out. So let's talk about critical values. Remember earlier, I told you that if we want to figure out where the derivative, where the graph reaches a maximum or a minimum value, we need to figure out where the derivative is 0 or where the derivative is undefined. So let's look at this graph here. Notice that as we move on this graph from left to right, it appears that we have a positive derivative, and then suddenly at C1, we have a 0 derivative. In other words, we have found in this case a maximum value. And then as we continue to travel down the graph, we have a negative derivative, and then we bottom out here at C2, which means C2 is a critical value. Anytime you have a derivative that is 0, you have a critical value. And then between C2 and C3, it seems that we have a positive derivative. And something interesting happens at C3. At C3, we have a vertical line, which means we have plenty of rise but no run, which means we would have a 0 in the denominator. So we have an undefined slope there, which means we have a critical value. And we will continue to climb here, and then we hit C4, which has a maximum value, or a 0 derivative in this case. And we go back down, and we have a negative derivative, and we hit this point here at C5. Here, the graph suddenly jerks to the right and goes back up, and this is called a cusp, C-U-S-P, cusp, which means the graph has done something sudden that causes that causes the derivative to be undefined. So if we leave C5 and travel towards C6, we have a positive derivative, and again, we have a maximum value. We have a cusp here because the graph suddenly jerks into the opposite direction. In other words, it goes from a positive slope on the tangents suddenly to a negative slope that causes a cusp, which is undefined, and that makes C6 a critical value. And we have a 0 derivative at C7, which makes C7 a critical value. And we're going to increase with positive derivatives here, and then we hit a 0 derivative at C8, which makes C8 a critical value. And then the graph is positive from here on out. So here's what the author says. Notice that the derivative is 0 when we get to C1, C2, C4, C7, and C8. In other words, those tangent lines would be horizontal, and we can see those in the graph here, here at C4, again at C7, and at C8. Notice that we have horizontal lines here, which means the slope is 0, and that makes those values critical. Notice that the derivative does not exist at the other marked locations. In other words, C3, the reason the derivative does not exist here is because we have a vertical line. And remember, vertical lines have undefined slope. If you look at C5, we have the graph going down and suddenly jerking up to the right, which causes a cusp. So that derivative does not exist. And if we look at what happens at C6, we have another cusp because the graph is going up and suddenly it jerks back down in a negative direction. So how do you find critical values? Basically, you look to see where is the derivative equal to 0 or where is the derivative undefined. Typically, we look for zeros in the denominator if we're looking for undefined values. And that's exactly what this definition here is saying. A critical value of a function f is a number c in the domain of f for which the tangent line is horizontal, in other words, we have a 0 derivative, or for which the derivative does not exist. That is, c is a critical value. That's the important part right here. C is a critical value if f of c exists and the derivative is 0 or it does not exist. And that value c, for which we have those situations create, those are critical values. So let's take a look at this bottom picture here. It says find relative maximum and minimum values. And if we look at the graph, we see that it's doing quite a bit here. It's going down, and suddenly it's jerking up. It's reaching a maximum point and dipping down and going back up again. So let's talk about what is happening with this graph. It says, again, we're looking for relative maximum and minimum values. Starting from the left, I will claim that this point here at C sub 1, I'm going to claim that this is a relative minimum value because relatively speaking in that area, it is lower than any other y value. In other words, if you look to the left, notice that the y values are higher. If you look to the right, notice that the y values are higher. So in that neighborhood, I would make the claim that the value f of C1 is lower than any other y value, relatively speaking. So this would be a relative minimum. This point here at C2 is a relative maxima because relatively speaking, it is higher than any point in its neighborhood. This point here is a relative minimum because it's relatively speaking in its neighborhood, it is lower than any other y value. And using the same justification, I can make the claim that this point here at C4 is a relative maxima, and then at C5 we have another relative minima. Probably should say for each one of those, they are either relative maximum values or relative minimum values. You really only should use maxima and minima in the plural. And I apologize for that. Sometimes I do get a little lazy in my speech, but I wanted to correct that before we move on. Okay, so let's move on to the next page. Theorem 2. Theorem number 2 says, if a function f has a relative extreme value on an open interval, then c is a critical value. In other words, the derivative is 0 or the derivative does not exist. And that may sound like we've already talked about that, and in a way we have. But in mathematics, oftentimes we will look at the statement written sort of backward to determine if the same thing is true. And if you read theorems 1 and 2, you will see that they are not exactly the same, although they appear to be. So if you're a wordsmith and you like to study words for word's sake and try to get a better understanding of theorems, you can go back and compare theorems 1 and 2. In other words, theorem 2 is sort of the converse of theorem 1. Okay, now for the mechanics of what we are doing. Let's go to the bottom of the page here and let's take a look at this graph. Notice that the graph is decreasing, then it reaches a relative minimum, and then it's increasing until it reaches a relative maximum, then it goes back down, and we hit a cusp here where the derivative is undefined. And suddenly we're increasing again, and then we are decreasing. Now that's talking about the characteristics of the graph. Let's talk about the characteristics of the derivative. So if we are between, say, here and here, not only is it decreasing, but the derivative is negative. And then in this blue interval here that I'm about to trace over, we're increasing, which means the derivative is positive, then it zeroes out, then the derivative becomes negative, then it becomes undefined. Then the derivative is positive, zeroing out here at this relative maximum, and then the derivative is negative. So what about the table here? Typically in a math textbook, tables give us a lot of good information. So I'm going to spend a little time talking about this table because students, particularly freshman students who do not have a lot of math experience at the college level, they would typically look at tables and move on. So I want to spend some time on this table here. So let's see what the first column talks about. The first column is just talking about a graph as x takes on different values from a to b. And notice that in each of these pictures, we go from a to b, right? A to b, a to b, a to b, and a to b. So that takes care of that column. And then in the second column, we are just looking at the y value at c. And they just want us to determine whether we have a maximum or a minimum value, or maybe we have neither. Let's take a look and see what the second column is talking about. Here it says relative minimum because if you look at this point here, relatively speaking, it's the lowest point in its area. In other words, any point to the right or to the left is higher. So that makes CF of C a relative minimum. Likewise, if you look here, we have relative maximum because if you look at this point here, when x takes on the value c, any y value in its neighborhood is lower. In other words, this point here is a maximum, a relative maximum. And then we have two cases where we have no relative maxima or minima in the neighborhood. And why would that be? Well, if you look at this point, when x takes on the value c, if you look to the left, it's lower than all of the points to the left, and it's higher than all of the points to the right. I think I said that backward. It's actually lower than all of the points to the left and higher than all the points to the right. Maybe I said that correctly to start with. It just didn't sound right. In other words, it's not absolutely the lowest nor absolutely the highest in its neighborhood. Likewise, if you look down at the very last row, if you look at this point here, notice that it's higher than all of the points to the left, but yet it's lower than all of the points to the right. So therefore, it is neither a maximum nor a minimum. And finally, we get to theorem 3. This is what we have worked our way up to. Theorem 3 is the first derivative test for relative extrema. The first derivative test is very powerful because it will help you root out where the graph reaches maximum and minimum values or undefined values. Now, I'm not going to read all of this in the box because, as you can see, it is very wordy. What I'm going to do instead is I'm going to let you study that as you review this section later. And I want to go straight to some problems to apply theorem 3. And then hopefully when you go back to study this section, it will make more sense. So let's talk about example 1. We're given this function here. It's a cubic. And as I said before, cubics tend to have this shape, especially if the leading coefficient is positive, which this one is. So cubic looks something like this. And it says to find any relative extrema. So the first thing we're going to do is we're going to have to take the derivative of the function and we're going to set it equal to 0 because I want to know where is this function reaching high and low points. So what is the derivative of 4x cubed minus 9x squared minus 30x plus 25? Well, if we use the power rule, the derivative is going to be 12x squared minus 18x minus 30. And the rest of this is really just algebra rather than calculus until we get to the very end here. But if we set the derivative equal to 0, then we can simplify and factor. Here, all they did was divide by 6 across each term. And once they got 2x squared minus 3x minus 5, they factored and they set the factorized version of this equal to 0. Okay, so 2x squared minus 3x minus 5 factors to be x plus 1 multiplied by 2x minus 5. Anytime you multiply two numbers together and you get 0, at least one of those numbers has to be 0. So either x plus 1 has to be 0 or 2x minus 5 has to be 0. If x plus 1 is equal to 0, then x has to be negative 1. Or if 2x minus 5 is equal to 0, if you solve that, x ends up being 2.5. We have now found two critical values. When x is negative 1, we have a 0 derivative. And when x is 5/2, we have a 0 derivative. What we typically do is we mark those critical values on a graph like this because we know the derivatives are 0. And then we look at what's going on everywhere else. And we do what they call test values. So if the graph zeroes out at negative 1 and 5/2, what's going on everywhere else? Well, if you pick a value in this interval, say negative 2, if you plug negative 2 into the derivative, you end up getting 54. In other words, if you plug negative 2 into this equation up here, which is the derivative, if you plug negative 2 into that, you get positive 54, which means you have a positive derivative. In other words, we have an increasing situation between negative infinity to negative 1. And then we know it zeroes out at negative 1. And then we pick a value between negative 1 and 5/2. 0, if you can use it, is always nice. So we use 0. We plug 0 into this equation here, and we end up getting a derivative of negative 30, which means it's decreasing. So what does that mean? Well, it means the graph reaches a 0 derivative, and then it decreases, and then it becomes 0 again at 5/2. But what about on the other side, the right side of 5/2? We can pick any number we want to between 2.5 and infinity, and the author chose 4 because 4 is in the interval. If you plug 4 in up at the top into the derivative equation, you get 90, which is positive, which tells me that the graph is increasing. And here we have a picture of the graph. And notice that, again, when x is -1 and y happens to be 42, we have a zero derivative. Likewise, when x is 2.5, we have a zero derivative, and we figured out that it's increasing on this interval because we used a test value and plugged it into the derivative formula. And then we figured out that the function is decreasing on this interval by testing a value. I believe we used 0. And then we did a test value on this side of the interval and figured out that the derivative was positive. In fact, they used 4 to figure out whether it was positive or negative. So let's take a look at example number 2. This time we have another cubic, and it's 2x cubed minus x to the power 4. I apologize, this is a fourth power, this is a quartic. And again, we're trying to figure out where does it reach maximum and minimum values. And what we do is the first derivative test, right? We figure out what the derivative of 2x cubed minus minus x to the power of 4 is. And if we do the power rule, we figure out that the derivative is actually 6x squared minus 4x. And of course, we will set that equal to 0 because we want to know where does the derivative zero out. Once we set it equal to 0, we can factor 2x squared out of both terms. And that leaves us 2x squared. And then in parentheses, we would have 3 minus 2x. And again, if you multiply two numbers together and get 0, at least one of those has to be 0, which means 2x squared would have to be 0, or 3 minus 2x would have to be 0. If 2x squared is 0, then if we solve, x would have to be 0. And of course, if 3 minus 2x is equal to 0, then we would add 2x to both sides, which means I made a mistake there. Let's try to fix that. If I add 2x to both sides, I would have 3 is equal to 2x. And then I would just divide both sides by 2. If I divide both sides by 2, I get x is 3/2. That gives me my two critical values, right? X is 0 and then x is 3/2. Those are my critical values. And again, we will put 0 and 3/2 on this chart here, right? As x goes from -infinity to infinity. I'm going to mark these two because I know the derivatives are 0 here. The question then becomes, what would the derivative be everywhere else? Is it positive or negative? That's what we want to know. And again, all you have to do is pick some test values. One value on each interval will suffice. And the author chose to use -1 to test this interval. When he plugged -1 into the derivative, he got 10. And of course, 10 is greater than 0, which means it's increasing on this interval here. It's increasing as x goes from -infinity to 0. And then the author picked 1 to test the second interval, this interval here. He used 1 because 1 is between 0 and 3/2. When he plugged 1 into the derivative, he ended up getting 2, which is positive, which means between 0 and 3/2, we have an increasing function. And then on the last interval, he chose 2 for the test value, which gave him -8. And that means that the derivative is decreasing on this interval because the derivative is negative. And here they just sum it all up in a nice table for you. And again, now that we have done the hard work, we can look at the graph and talk about that. So what have we determined here? Well, we figured out that when x is 0, this thing has a horizontal tangent. And when x takes on 3/2, we have a horizontal tangent, which means the derivatives are 0. And then we tested the other 3 intervals. We figured out that it's increasing from -infinity up to 0. And then we figured out that it's increasing here and then decreasing here. Now let's take a look at example 3. This function is rather unique. We're multiplying x squared times e to the power of x. Of course, there is a graph associated with that. And by the way, I haven't talked about this, but there's a graphing application out there. You can download the app or you can use your PC, but it's called Desmos, D-E-S-M-O-S. And Desmos is a graphing tool that is second to none. It is one of the most prolific graphing tools out there. It's absolutely free. But if you will go to desmos.com or download the app, you can enter these functions and look at their graphs, and it will save you a lot of time in trying to figure out where the derivative is 0 or undefined. Now you may be wondering, how in the world do we find the critical values? Well, it's the same process. All you do is take the derivative and set it equal to 0. Of course, in this case, we have a product, so we have to use the product rule. In this case, we would multiply the first function times the derivative of the second, plus the second function times the derivative of the first, and we would set it equal to 0. Notice that we can factor out x e to the negative x, and that leaves us negative x plus 2 in parentheses. And again, we just set both of these equal to 0 and solve. That gives us 2 critical values. X can be 0 or x can be 2. And they follow the exact same procedure as before. They figured out the critical values are 0 and 2, so they mark those here on this horizontal line, and then they pick numbers in each interval to see whether or not the derivative is positive or negative. So on this interval here, they chose to test -1. So they plugged -1 into the derivative equation and got -3e, which is, of course, less than 0. Which means it's decreasing on this first interval here. Then between 0 and 2, they chose 1 as their test value, and they plugged that into the derivative equation and got e to the power of -1. Of course, e to the power of -1 is actually 1 divided by e itself, which is positive. So we end up getting a value greater than 0. And then they tested 3 on the last interval, and they figured out that the derivative is negative, which means it's decreasing on the last interval. And if you look at the picture, you can see that it is decreasing until x becomes 0, and then it's increasing until x reaches 2, and then it zeroes out, and then it's forever decreasing. The only thing I'm going to say about example 4 is you have to keep in mind that not only do you set the derivative equal to 0, but you need to figure out what values of x will make the denominator 0, because you cannot divide by 0. And if you look at example 4, once they take the derivative, they realize that they have a fraction and the denominator cannot have a 0. In other words, in this case, x cannot be 2 because 2 minus 2 is 0. In other words, the derivative is undefined there. In fact, that's the only place where the derivative is undefined. So what they did was they just marked that critical value, and then they did test values on these two intervals to see whether or not the derivative is positive or negative. So they chose to use 0 on the left side, and that gave them a negative number, which means it is decreasing on the first interval. And then they plugged in 3 for the second, or the right side, and they got a positive derivative. So it's actually decreasing, as we can see in the graph, and then it's increasing. And we have a cusp at x is equal to 2. Okay, the second half of this lecture is going to be about the second derivative and how we can use that to sketch more accurate graphs. Now, you will recall, hopefully, in the first part, we can use the first derivative to figure out where the graph reaches perhaps a relative maximum or a minimum. For example, if we look at this graph here at problem number 1, we can tell that we have a relative maximum here and we have a relative minimum here, and the derivatives are 0 at those 2 points. If you look at problem number 2, here we would have a horizontal tangent, which means the derivative is 0 at this point. And also here, we have a relative minimum, which means the derivative is 0, and that appears to be at 2. So therefore, we can use the first derivative to get a general idea of what a graph looks like. And in the second part, we're going to look and see the power of the second derivative to determine the shape of a graph as well. I'm going to go ahead and switch over to the next page here. Just as a sort of review, let's talk about these two graphs at the top of the page here. We can see that the derivative is negative to the left as it's coming down, and at some point this thing zeroes out with a 0 derivative, and then it goes back up. And if you look at the one on the right, we appear to have a positive derivative, and then it levels off at 0, and then it becomes a negative derivative from there on out. But what they want you to realize here is what's happening with the second derivative. The second derivative is positive, it's greater than 0. And anytime the second derivative is positive on an interval, that means that it's concave up. In other words, it is sort of bowl-shaped on that interval. If you look at the one on the right, the second derivative is negative. And anytime the second derivative is negative on a given interval, that means it's concave down, which means it's sort of an inverted bowl shape. And those are the main ideas for the second section. So let's look at this definition here in the middle of the page. Suppose that a function has a derivative at every point in an open interval. The function is concave up on the interval if the derivative, the second derivative, is increasing over the interval, and it's concave down on the interval if the second derivative is decreasing on the interval. In other words, it's negative. And that leads us to theorem 4, a test for concavity. If the second derivative is positive, for all x values on an open interval, then the graph is concave up. And if the second derivative is negative for all x's on an interval, then the graph is concave down. Let me give you a sketch here to the right that sort of explains what's going on. If I look at this point here on the graph, I'll mark it in black. This point here would have a positive first derivative, and it would have a negative second derivative. it would have a positive first derivative because if you look at the slope of the tangent line, it would be positive. And the reason I know it has a negative second derivative is because at this point, it has sort of a inverted bowl shape. If you look here, the first derivative is positive because if you put a horizontal tangent on it, it's positive. And the second derivative here is also positive because it has a bowl shape to it. This page here, again, makes the same observations. If you look at the graph in this piece here at the top left, it's concave down. It's concave down, and what does that mean? Well, if you look at it, this is a decreasing function as you read from left to right. It's going down, it's concave down, and the function is decreasing. On the right, we have concave down, and the function is increasing. If you look at the bottom left, we have concave up, yet decreasing as it moves from left to right. And then this graph here is concave up and increasing from left to right. So what does that tell us? Well, since it's concave down, the second derivative has to be negative in both of these instances here. And on the bottom row, since both of those are concave up, that tells us the second derivative is positive. Now let's look at the columns. This column says that every graph in this column has a negative first derivative, which means it has to be, it would have to have a negative slope at any point. So we would have negative tangents here for any point. And likewise below, you pick any point on that graph and I will show you negative tangents. If we look at the right column, notice that we would have, you pick any point here and you would have positive tangent lines, right? Those would have positive slopes. And also down here, we would have positive slopes. So the first derivative here would be positive and the second derivative positive. For the bottom left, we have a first derivative that's negative, second derivative is positive because it's concave up, and so on. Let's go to this bottom picture on the left. If I pick at any point on the open interval between A and C, I pick any point between here and here, notice that the first derivative would be negative because it's decreasing. It has negative slopes for any tangent lines you may pick, but it's also concave up, which means the second derivative would be positive. In fact, if you look over here, at this point, the second derivative would still be positive because it's concave up, and the first derivative would also be positive. If you look at this graph on the right, if you pick any point between A and C, say this point here, this would have a positive first derivative because if you were to draw a tangent line, its slope would be positive. But since it's concave down, the second derivative would be negative. If you pick any point over here on this open interval, the first derivative would be negative because it's going down. It would have negative slope. And since it's concave down on that interval, the second derivative would also be negative. Let's talk about Theorem 5 quickly here. The second derivative test. The second derivative test is the test for concavity, and it works like this. If you set the second derivative equal to 0, that will create intervals, and then you can, upon inspection, determine whether or not the graph is concave up or concave down. It's a lot like doing the first derivative test. The first derivative test tells you whether or not the graph is increasing or decreasing, whereas the second derivative test will tell you whether or not the graph is concave up or concave down on a given interval. Just for clarification, let's go through another graph and discuss the characteristics of it. Let's look at this graph on the right. I'm going to pick a few points. I'm going to pick a point here, and I'll pick a point here and a point here. It appears to me that it's concave down from negative infinity all the way up to -2. So from negative infinity to -2, I would say it's concave down. And then if you go from 2 to infinity, it's concave up. Since it changes concavity here at 2, that is called an inflection point. An inflection point is where a graph changes concavity. So how would we do this in a manner similar to the first derivative test? Well, you would take the second derivative and set it equal to 0. And when you take the second derivative and set it equal to 0 and factor and solve, you will find in this case that when x is equal to 2, the second derivative is 0. And then you just test values to the left and to the right to determine what the concavity is. Let's take a look at example number 1. It says find any relative extrema and graph the function f. Okay, so this is our function. And again, if I were you, I would go to Desmos.com and I would type this graph in and take a general look at it. If you take the first derivative, you get 3x squared plus 6x minus 9. That's just power rule. And we would set the first derivative equal to 0. When we set the first derivative equal to 0, if we divide through by 3, we end up getting a simplified version of the derivative. And then we would factor it. Notice that it's still set equal to 0. And again, anytime you multiply two numbers together and get 0, one of the numbers has to be 0. In other words, x plus 3 would have to be 0, or x minus 1 would have to be 0. If x plus 3 is 0, then x is equal to -3. If x minus 1 is 0, x has to be +1. So those would be our critical values. And in this case, they went ahead and plugged in -3 and +1 into the original equation just to figure out where the critical points are on the graph. So one of the critical points is at -314, and the other critical point is at 1, -18. Then they took the second derivative. The second derivative is 6x plus 6. Normally, the second derivative is a lot easier to work with. What they chose to do was they chose to go ahead and plug in the -3 and the +1 to determine whether or not it's concave up or concave down. And if you plug in -3, you get -12, which is less than 0. So that means it's concave down at that point. And then when they plugged in +1, they got 12, which is greater than 0. And that lets me know that this graph is concave up at that point. So let's take a look at the graph, and hopefully it will make more sense once you see it in pictures. But notice that the point 1, -18, using the first derivative, we figured out that those were critical points, and then we plot those points on the graph. And then we look at the second derivative at those points. When they plugged -3 into the second derivative equation, they got a negative answer. And they knew that from this point, it had to be concave down at that point. When they plugged 1 into the second derivative equation, they got a positive answer. I believe it was 12. And that means it's concave up at that critical point. And we know that the derivative is never 0 or undefined again. That means the graph has this shape here. Now, when you took Algebra 1 and Algebra 2 in high school, your teacher probably told you to either use the graphing calculator to figure out the graph, or they made you plot so many points that it drove you crazy. Well, in calculus, we only have to graph a few critical points to get an idea of what the general graph looks like. Let's look at example number 2. Here we have a function. It's difference between two exponential functions. And again, they just want to know about the highs and lows on the graph. So they took the first derivative and set it equal to 0. And then they factored out e to the x, leaving 2e to the x minus 1. And again, you just have to try to figure out, okay, what values of x would be 0? Well, there's no value of x you can plug in for e to the x to get 0. So the question is, for what value of x would 2e to the power of x minus 1 equal 0? And if you solve, you realize that x would have to be the natural log of 1/2. So the natural log of 1/2 ends up being our only critical point on this graph. And then they took the second derivative. Excuse me. The second derivative is just going to be the derivative of the derivative. So they took the derivative of k prime, which gave them 4e to the power of 2x minus e to the x. And again, they just plugged in that critical value, the natural log of 0.5. They plugged that into the second derivative, and they ended up getting 1/2, which is positive. So that means that the graph has to be concave up at that point. So let's see if we can find a graph that illustrates that. Yes. If we take a look at this graph, we can see that the natural log of 1/2 is the x value here. And if we plug that back into the original equation, the original function, we realize that the y value is -1/4. So that allows us to plot with accuracy where the critical point is. And then all they did was they plugged in the natural log of 1/2 into the second derivative, and they figured out that since it's positive, the graph is concave up. That means this graph is forever concave up, and it has sort of a bowl shape here. On this side, it's not as obvious because this may look straight, but it's actually not straight. If we were to zoom in tighter and tighter, we would realize that that's still concave up. And as I said earlier, points of inflection occur when the graph changes concavity. Notice that here we have concave down, and suddenly it becomes concave up. And in between there, somewhere in the middle, is the point of inflection. Same thing with the graph in the middle. We're concave down, then we're concave up, and there's the point of inflection. Concave up here, suddenly concave down, and again, point of inflection. And notice, as it says here, the point of inflection on the left has a second derivative of 0. And over here, the second derivative at that point is 0. And then in the middle, the second derivative does not exist. And remember, we typically look for x values that would give us a 0 in the denominator in order to find those that do not exist. Theorem 6. Finding points of inflection. If you want to find possible points of inflection, you set the second derivative equal to 0 and solve, or you look for x values where the second derivative does not exist. Let's take a look at that with example 3. With example 3, I think I'm going to go after just part A. We want to know where are the points of inflection for this function here. So how do we find the points of inflection? Well, we will set the second derivative equal to 0 since this is a polynomial. And remember, probably from high school, that polynomial equations are going to be defined everywhere. There's not going to be a situation where you have a point of inflection at an undefined value. So continuing with problem A, 3A. Just to talk our way through this one. It says in example 1, the second derivative of x cubed plus 3x squared minus 9x minus 13 ends up being 6x plus 6. They did that earlier for us. And if you set the second derivative equal to 0, in this case, x is equal to -1. And if you plug -1 back into the equation, you will see that -1, -2 is the point there. And we just want to verify that it is a point of inflection. So pick any value of x to the left of that point, and then pick any value of x to the right, and you can test to determine whether or not this did indeed change concavity at -1. They chose to use a test value of -2 for the left side, and then they chose to use 0 for the right side. When they plugged in -2 into the second derivative, they got -6, which is of course less than 0, which means it's concave down. And then they plugged in 0 again for the right side. They got +6, which is greater than 0, which means it's concave up on the other interval. So once you find the inflection point, you can test anywhere to the left and to the right to determine that it did indeed change concavity. And even though I'm not going to go into details on the second part, it's the same concept. You have your function, you look at the second derivative, you set the second derivative equal to 0, then you get involved in the algebra, and you get your critical value. And again, you pick values to the left and to the right. A little word of caution here. Some people get stuck here and they don't know what to do. The natural log of 1/4 is just a decimal, and if you plug that into your calculator, they will convert that for you. So all you really need to do is pick a test value to the left of -1.386. I would say choose -2. In fact, that's what they did. And then pick a value on the right side. If you can ever use 0, use it. And they plugged in -2 and 0, and they figured out that it's concave down on one side and concave up on the other side. Okay. I believe earlier I made a mistake and said this was forever concave up. It does actually change concavity there. Okay. Now, instead of redoing this entire video, I'm going to say this. Just because the second derivative is equal to 0 does not guarantee that you have found an inflection point. In fact, I'm going to take advantage of this mistake that I made on the previous page and say, if the second derivative is equal to 0 at a point, you have found a possible point of inflection. You must test those values on both sides to make sure that it changes concavity. And I assumed that it did not change concavity, and actually it does. So setting the second derivative equal to 0 will find potential inflection points. There's no guarantee there. So I'm going to take that mistake and I'm going to own it and make it a teaching opportunity. If I had to pick a table in the entire section to focus on, it would be this table here. It's the table that goes through curve sketching. Sketching curves involves several different things. You would need to look at the first and second derivative. You would need to consider the domain values. And again, typically for this class, the domain is going to be all real numbers except for those values of x that would give you a 0 in the denominator. There are other exceptions, but I'm not going to go into those today. Once you look at your derivatives, you need to find your critical values. And you can use the first derivative test to determine whether or not the function is increasing or decreasing. That will also tell you whether or not you have relative maximum or relative minimum values. You can find possible inflection points, and I will underline this, determine candidates for inflection points. So again, setting the second derivative equal to 0 does not guarantee that you have found an inflection point. It guarantees that you have found a potential or a possible inflection point. You must do the test values on both sides to determine that it does change concavity. Once you determine concavity and you've looked at the critical values and found the highs and lows, you can then sketch the graph. So let's take a look at that, because this is going to sum up everything we have pretty much learned in this lecture here with example 4. Okay, so we're looking at x to the power of 4 minus 2x squared. This is going to be a quartic. And let's take a look and see if we can't figure out the general shape of the graph. The first thing we're going to do is we're going to look at the first derivative, and we're going to look at the second derivative. Again, this is going to give us an idea of where we have maximum and minimum values, and it's also going to help us to determine concavity. Okay. So what is the derivative of x to the 4th minus 2x squared? If I use the power rule, the first derivative is 4x cubed minus 4x. And if we go ahead and find the second derivative, that's going to be 12x squared minus 4. Luckily, these functions are all polynomial functions, which means all real numbers is the domain. There are no illegal values for x. The next thing we want to do is we want to find the critical values. That takes us to part B. So get used to going through these steps in order, and that will help you. I tend to, because of my experience, I tend to jump around, which probably causes more mistakes than it's worth. So I probably should go through these in the same order as well. But sometimes I get in a rush and I assume things I probably shouldn't. So let's go through it just like they advise us to here. So let's look for critical values. To find critical values, we set the first derivative equal to 0. In other words, 4x cubed minus 4x is equal to 0. Here they factored out a 4x, and that left us with 4x multiplied by x squared minus 1. And x squared minus 1 is a difference of squares. It will factor to be x plus 1 times x minus 1. And that means for 4x to equal 0, x would have to be 0. And for x squared minus 1 to equal 0, x would have to be either negative 1 or 1. So we have found 3 critical values. And notice that they went ahead and plotted those points. How did they get the y values? Well, they just took the y values and put those into the position equation here. They just plugged in 0, 1, and negative 1, and they figured out the y values, and they were able to plot those 3 points. So let's go to the second part. And again, we're just working our way down through the table. For the second part, we want to determine whether or not this graph is increasing or decreasing, which tells us whether or not we have highs or lows at those points. So they took x as negative 1, which is a critical value, and they looked at the second derivative, and they got 8. Well, 8's greater than 0, which means it's positive. And that means at negative 1, it's concave up. So they went ahead and made it concave up here. Then they plugged in 0 for a test value. They plugged 0 into the second derivative. They got negative 4. And since they got a negative, they know it's concave down at that critical value. And finally, they plugged 1, the last critical value, into the second derivative, and they got 8, which is positive. And since it's positive, they know that when x is positive 1, it's concave up. We know from the first derivative being set equal to 0 that there are no more 0 derivatives, which means there are no more highs or lows. And the last thing they want us to look at are the possible inflection points, which takes us to this point here. Remember, in order to find possible inflection points, you have to set the second derivative equal to 0. They set the second derivative equal to 0, and notice the algebra gets to be a lot of fun. And they found two values. X is equal to plus or minus 1 over the square root of 3. Those are the two values that are potential inflection points. And we know from experience from our previous points on the graph that these are inflection points because it's concave up and then concave down, and then concave up. So our inflection points are located here and here. And this is the finished graph on the top right. Now I'm going to walk you through example 5, and we're going to leave it at that. We'll take a look at the graph at the end, and hopefully you can rewatch this video. I plan to post some additional videos to help you with the first and second derivative tests, and then you can get started on the MyMathLab work. Let's take a look at example 5 very quickly. We have a function. It happens to be a natural log of x squared plus 6. At first, we hesitate and go, oh my gosh, it's been a while since we've done these. So go back and review the formulas for derivatives of natural logs. And this is the first derivative. And this is the second derivative. And luckily, the domain is all real numbers because there's nothing we can plug in for x that will make this denominator 0. X squared plus 6 can never be 0. There's nothing you can plug in. Any number squared is going to be positive or 0. We cannot make x squared negative 6, so we have really nothing to worry about as far as the domain. So you take the first and second derivatives, and then you're going to set each of those equal to 0. I'm sorry, you're going to take the first derivative and set it equal to 0. Once you do that, you solve, and you will figure out, in this case, your critical point. And you will plug that critical point back in, and you will determine if it's increasing or decreasing. If you set the second derivative equal to 0, it will tell you whether or not you have potential inflection points, and you will have to investigate that. I will leave all of that for you to read and think about. But I do want to look at the graph, and we will close with that. Notice they did go ahead and look at concavity based on the results from the second derivative being 0 and test values, and then they were able to sketch. So what do I know from this graph? This is going to sum up everything. The hardest part about this, in my opinion, from teaching calculus for almost 30 years, it's the algebra that will bog you down. It's really not the calculus concepts. And you've probably heard me say that, and by now you're probably rolling your eyes and saying, we get it. But I want to emphasize that the enemy here is not calculus. It's typically the algebra, and that applies to me as well. Sometimes the algebra gets to be very overwhelming. But I want to focus on the sketch because we've learned quite a bit in these two sections, and what we have learned will allow us to have some meaningful conversations using mathematical terms about what is going on with graphs. I know that at this point here, we have a 0 derivative. I know that if you look to the left of that 0 derivative, you will have a decreasing function, which means the derivative is negative for all of the values to the left of 0. And for any x value I plug in to the right, it's increasing, which means the first derivative is positive. That's what we learned from 3.1. Then we were able to figure out that if you set the second derivative equal to 0, you can find possible points of inflection. So if you set the second derivative equal to 0, here is one possible point of inflection. And here is another possible point of inflection. And if you plug in test values to the left and right, the immediate left and right, you will figure out that it's concave up here. And believe it or not, it's concave down here. It's very subtle change. If you were to zoom in, you would see that it changes concavity, concave up and then concave down. It's a very nuanced change there. That takes care of the first derivative test and the second derivative test. I hope that you found this video lecture to be useful. Again, I'm going to post this for you to watch at your leisure, along with some other helpful links. If you have any questions, feel free to reach out to me. If you would like to screenshot a problem that is bothering you, you can email that to me. I'll be happy to get back with you and give you at least some hints on that. Thank you.